Alright, hey guys, this is James, one of the undergraduate tutors, and I'm going to be going over problem set 6, question number 5C, per request. Oh, sorry about that. There we go. So question 5C. So this question is basically asking us to calculate the configurational entropy change for the following process below, right here. So a few things we should note is that the system is occurring in a large volume, right? So what this is saying is that M is much larger n, or it allows us to assume that M is much larger than n since it's occurring in a large volume. And along with that, we see that n and M are both large numbers, right? N is referring to number of molecules. We see here 6.022 times 10 to the 23rd ATP. This one is 2 times that. So what we can say from that, or what we can use from that, is we can use the simplification of the multiplicity formula, which if you recall is lnW is approximately equal to n ln m over n. So that's the first thing we should note. The second thing that's important to note is that the change in entropy is equal to S final minus S initial, which is equal to R times ln multiplicity final minus multiplicity of initial. So recall that multiplicity is directly related to n and m, as we see here, right? So for the initial system, our multiplicity is actually, or our n, so n is number of molecules for ATP is equal to 6.022 times 10 to the 23rd, which we'll call Avogadro's number, Na. Along with that, in the final, we see that we have two different molecules. Our first one is N-ADP, which is 6.022 times 10 to the 23rd molecules as well, which is equal to Na. And then NPI is also equal to 6.022 times 10 to the 23rd, which is also Na. So we see here that the molecules we're dealing with are all equal to Na, right? Along with that, with the final system, since this is such a large volume, we can assume that the molecules of ADP are independent to the molecules of PI. So what that ends up giving us is the W final is equal to W of ADP times W of PI. So yeah, so from there, let's plug in what we know into this formula here. So we have so let's deal with S initial first. So S initial is equal to ln W initial, right? Which is basically just ln of the ATP, ln of the multiplicity of ATP, which is equal to N ATP ln M over N ATP. But then recall that N is equal to Na. So I'm just going to start using Na for all of these, right? So I'll rewrite this as Na ln M over Na. Oh, I also forgot, should be an R right here, R right here. So let's go into the final final entropy as well. So ln final is equal to W ln W final, or R ln W final, which is equal to R times ln W ADP plus ln W PI. Because these terms multiplying when we take the natural log, it's just the additive, or it's just the sum of the natural logs. So what we're left here is that S final is equal to R times N ADP ln M over N ADP plus N PI ln M over N PI. So we already said that these are equal to Na, right? So we can simplify this further. We can say S final is actually equal to R times 2 since these two are the same value, since they're both NADP is equal to NPI, which is equal to NA, right? So we can say it's actually times 2R NA ln M over NA. So we have this so far, right? And then we see that what we see is entropy of the final is essentially 2 times the entropy of the initial. So furthermore, if we look at the question, it says the scientist estimates that the molar entropy of ATP under given conditions is 200 joules per mole Kelvin. So from there, we can say that S initial is equal to 200 per mole or joules per mole Kelvin, which is also equal to NA ln M over NA. All right, so we have all this. We have this. We have, so this is the value of the initial entropy. Then we have the final entropy, right? Here. So let's plug this back into our original change in entropy formula, right? So we have delta S is equal to final, so that's 2R NA ln M over NA, minus initial, which is R NA ln M over NA. So when we simplify this, this gives us R NA ln M over NA, which if you look back right here, oh, one big thing I forgot, I keep forgetting the R, that's my bad. So if we look back here, we see that R NA ln M over NA is actually equal to 200 joules per mole Kelvin. So our change in entropy is 200 joules per mole Kelvin. So from there, the next part of the question is asking, is this sufficient to account for your answer in part B? I believe the entropy change for the hydrolysis reaction in part B was 133 joules per mole Kelvin. And since 200 is greater than 133, we can say that the entropy change is sufficient to account for the observed entropy change. Hopefully this makes sense. Let me know if you guys have any questions. All right, thanks for watching.